and welcome to this talk by Enigma. Um, I'm happy to be here. I'm based in Boulder, down the or up the road, but I acknowledge that some of you might be traveling from near and afar, and it's always good to see to talk to people in person and be on the same room. So, welcome to this talk. Hopefully, you'll get something out of it. There's this quick link that points to an article where there's a bunch of resources that will be relevant to most of this talk. So I just want to start with a quick comment in that research shows that people attending talks like this usually walk away retaining at most 3 key ideas. So I want to make it really easy for you and explicitly say those 3 key ideas that I'd like you to walk away from this talk. And one is that privacy equals Enigma in the Ethereum ecosystem, and that's about the first third of my talk. Key idea number 2 is that analogous to Ethereum smart contracts, we have this notion of secret contracts where we'll talk about privacy. And those secret contracts are written in Rust. And then finally, in order to develop those secret contracts, we provide a truffle-like environment. So if you are familiar developing contracts in Ethereum, you should feel like a very familiar environment here to hack on Enigma. So we acknowledge that blockchains have a privacy problem in that all information that we commit to blockchains are public by default. And we believe that this greatly limits the potential applications, or limits potential applications in that you cannot compute over sensitive data. So Enigma is solving exactly this problem where we enable using sensitive data in your applications without compromising on decentralization. So, and we provide these 2 layers. You can think of a sidechain to Ethereum in which we have the Enigma network that runs on nodes with trusted execution environments, which is a special hardware technology that is now fairly commonplace on all Intel machines that enables the network to compute over encrypted data. And then we use Ethereum for verification and reaching consensus. And this separation of computation on one layer and verification on Ethereum allows for greater scalability than what is possible right now. So Enigma Discovery is going to be the first launch of our network that will publicly enable secret contracts, and that happens on a permissionless network. It's economically incentivized, like in a proof-of-stake type of network. And most important to this talk and this event is that it is fully compatible with Ethereum. So you can develop your standard dApp that you might be already working on, but have a privacy need, and you can offload those privacy computations onto Enigma. So first I want to introduce how Enigma works, and I believe that the best way how to do this is by telling the story from the perspective of the different stakeholders that participate in the system. So very much like Ethereum, we care a lot about the users that participate or that use these dApps, the developers that deploy those dApps on the network. And analogous to the miners, we have the workers that execute the tasks. So we start with developers writing secret contracts that I alluded to before, compile them to bytecode, and send them to the Enigma network. And those contracts that live on the Enigma network are registered on a smart contract on the Ethereum blockchain that manages them. So these are the two layers that I mentioned at the beginning, where we have a computation layer and a verification layer. The way that users interact with the dApps is by submitting encrypted data to the network. That creates tasks. Then a hash of the metadata of the task is also sent to the Enigma contract on Ethereum for housekeeping purposes or for accounting purposes, and then the task is sent to the network. Then workers in the network receive tasks based on a stake-weighted lottery. The selected workers execute those tasks and disseminate the results across the network, and the worker submits the results to the Ethereum, and once that task is verified, then payment is released to the worker in compensation for computing that task. Let's talk about the execution model a little bit more in depth. So for every secret contract, there's an encrypted state that is maintained in the network. And the user encrypts their inputs to the network, which are only decrypted inside this trusted execution environment. You can think of as a black box that lives within the processor of that computer, that not even a person who has absolute and physical control of the machine can access into it. So it's a pretty neat technology that Intel introduced about 4 or 5 years ago, but we believe that it hasn't really reached mainstream in terms of applications, and this is a really interesting use case for that technology. And I believe that for any laptops and computers manufactured after 2015, 2016, it's already comes in by default to the CPU. So then the worker is able to decrypt those inputs with a key that only it knows, and updating the state, send it encrypted to the network, and then send an encrypted output to the user if that computation produces any outputs. And also you can have Ethereum callbacks where, depending on the output of that task or that computation, you can trigger events on Ethereum. So acknowledging that this is, a hackathon and you might be thinking about what to build, I want to think about or talk a little bit about what can you build here in ETHDenver with Enigma technology. And we are sponsoring 3 prizes, one specific to games, one specific to a coin mixer that we have developed, and then another one that is essentially open to whatever wild ideas you might have. So think about games that require you to hide actions, like in the simplest form, rock, paper, scissors, or battleships, quiz or war competitions like Jeopardy or Hangman, scavenger with secret locations or secret messaging. And I want to highlight, so here in Enigma there are 5 of us here at ETHDenver. I want to highlight 2 people there in the back, Ainsley and John, who are from our business development team and the people who are constantly thinking about potential use cases and applications of this technology. So if you have any ideas, I highly, highly, highly encourage you to run them by them and have a little bit of a brainstorming session, because they will be able to provide a lot of feedback. They probably have thought about similar ideas before and will be able to support you in many ways. So because this is a hackathon and we want to get our hands dirty with this technology, what I want to do now is guide you through the steps of developing a secret contract, and I might run out of time before I go over the interaction with the secret contract. But so secret contracts, I mentioned that it's in Rust, and we are following the ETHDenver circuit. We were at ETH Boston, ETH Waterloo. Here we are again, and typically developers is like, Rust, why another language? It might not be the easiest to hack onto in a hackathon, but as you might expect, if we are building a cryptographically secure protocol that gives a lot of privacy guarantees, we have to choose a language that is good for that, not that is easily hackable. So hopefully you appreciate that choice on our part. Most important, so Rust is similar to C, but is memory safe. You cannot have buffer overruns, you cannot have memory overflows, you just can't. You don't lose track of pointers. The language doesn't allow it. It has a very good performance, again, similar to C. It has a great package manager and a wonderful community. So, I think it's worthwhile mention that it's the most loved programming, and it must be for something. So if you are getting into Rust over this weekend, I can assure you that you'll find a lot of support through online forums and a lot of documentation and a lot of people on chats and such that will be more than happy to help you out, in addition to the support that we can provide. So I want to walk through the example of building on the millionaire's problem. For those of you not familiar with it, it's also known as Yao's millionaire problem, in which you have two or more parties that want to know who's the richer, but they don't want to disclose the amounts to each other, right? So this is a schematic of the problem where we create a secret contract for a millionaire's problem. Bob submits his entry with his wealth encrypted to the contract. Then comes Alice and also does the same, and the contract decrypts those encrypted inputs, computes the richest, and returns the output. In this case, the output is not encrypted, so that each of them know the result. Another good thing that you should know is that we have 9, 10 secret contracts already developed and on our repo. So even if you know nothing of Rust and you are not willing to learn much of Rust this weekend, I can almost guarantee that almost by copy pasting you can get a long way. So just browse these other examples where we have tried to cover most of the functionality that secret contracts can do, and just hack your way along by copy pasting. So this is one of the contracts that we have there, and I want to go almost line by line, demystifying how hard this can be. If I remove the comments, I think it's about 20 lines of code. So I think that anyone can deal with 20 lines of code. So Rust, the version of Rust that runs inside those enclaves does not provide all the standard functionality of Rust. So in the first line, we remove the standard libraries. Then we bring packages into scope, and this is the glue between the runtime and the contract. ENGWASM allows reading and writing from the state. Then this other package allows interactions with Ethereum, and this third package allows serialization and deserialization of custom data structures in and out of the secret contracts. So these 23 or these lines you just copy paste, don't have no questions asked. So then we're going to make use of the encrypted state, which and we need a key. We need a string that will act as a key to that hash map on the state, and then we declare our data structures, and we do this in this fashion where this struct will have two fields, an address and an integer that will hold the address of the user and the net worth of that user. And there's a one-to-one mapping to, these are H256 is a hash of 256 bits, that's 32 bytes, which is equivalent to the Solidity address fill. And the other one is an unsigned integer of, again, 32 bytes, similar, that maps to an unsigned integer of Solidity. There's there's a one-to-one equivalency of most of the types in our documentation. Then we declare the public functions that will be accessible on this contract. There will be two. One is to add a millionaire, takes 2 arguments, and then is the compute richest that takes no arguments but returns an address. We initialize the public struct that will contain both the public and private functions. We declare private functions in this way, where we'll get the millionaire, we'll read from the state to get the millionaires that may have been stored in the state. And then we declare that one of the 2 public functions add a millionaire that takes an address and the amount. And we first read into the state, get all the millionaires, if any, that are. We create a new millionaire, and then we push it into that vector that we got from the state, and we write it into the state. So it's fairly logical. You might need some help with the semantics of specifics to Rust, but again, following examples, most of the functionality that you will need is read and write from the state, run your computations, and return a value. So that's a good example. And then again, at the end, we're going to compute the richest. So here we make use of some very specific Rust language, where we get the millionaires, we iterate of the array that we get, we find the maximum by the amount key, and we return that in the address. And if we get nothing out of that search, because maybe we are calling this function before we have entered any millionaires, we just return an empty address. So let me see what I'm doing in time. As I said, so that covers writing a secret contract in Rust. Then we provide a development environment, a Docker network that you can launch into your own machine. I mentioned before that Enigma network relies on these trusted execution environments that are specific to some hardware, but we provide a simulation environment where you don't need any specific hardware, or you don't need to worry about that. You can develop freely without worrying about hardware requirements, and knowing that the privacy guarantees will come when you deploy this contract on testnet or mainnet. So that's what the Docker environment looks like when you launch it by discovery start. And analogous to Truffle, as I said before, you run discovery compile or discovery migrate to compile those secret contracts and to migrate those contracts over the network where you can interact with them. So I'm going to leave it here. I want to make sure that I have time for questions. We have a table up there. Some of us will be there all the time, so if you need any help, come and talk to us. Any questions? Nope. Great, all clear. I hope you got those 3 ideas. Privacy equals Enigma in Ethereum. Secret contracts are written in Rust, and we provide a Truffle-like development environment to make it easy for those of you who have been developing smart contracts, to start hacking on Enigma. That's it. Thank you.
Thank you, Victor.